Hello and welcome to the logic of it all. In this video, we are going to take a closer look at Venn diagrams and one of their applications. We have these equalities between sets that are called set identities. We looked at some of these in the previous videos. For example, if we take the union of a set with itself, A union A, we get back A, no matter what A is. Same for intersection. If we take the union of any set with the empty set, we get our set back. And if we take the intersection of any set with the empty set, because the empty set doesn't have any elements, it doesn't have anything in common with any other set either, so the intersection of empty with anything is empty. So if we think about the definition of the operations union and intersection and the empty set and so on, these set identities are more or less obvious why they hold. But there are other set identities that are not as obvious. So here's an example. If we take the union of A with A intersection B, we get back A. So this is at least not as obvious as the ones above. So we need some kind of justification for accepting this. And Venn diagrams give us not a proof, but somehow like a proof by picture kind of argument for set identities. So for the rest of this video, we are going to work through some examples of set identities and how they can be justified or proved in quotation using Venn diagrams. Our first set identity is A union A intersection B is equal to A. So what I'm going to do is I'm going to do this step by step. So if this is my universal set, and this is A, and this is B. So what I want is the union of A with A intersection B. So again, step by step. Let's first figure out where A intersection B is. So if you remember, the area that is common between the two, or the overlap, is the intersection. So the red area is this. So this is the red area. Now A, that's obvious, right? The entirety of A, I'm going to use a different color for A. So anything that is inside the circle representing A, including the red area. So this is painted blue. Now we are taking the union of every surface, that is painted blue together with everywhere that is red. Now, if you think about it, what would be the intersection? The union of the two, right? So if you take the union of the two, you get back A. So this is A. So in this case, in this diagram, I've painted A. In this diagram, this is for A union A intersection B. And obviously we see that the same area is painted, so it means that these two sets are equal. So that's kind of like proof by Venn diagram. Again, it's not an exact mathematical proof, but some type of justification for the set identity A union A intersection B is equal to A. Here's another example. The difference between A and B, A minus B, is equal to the intersection of A with the complement of B. So what I'm going to do is I'm going to do one Venn diagram for this set, another Venn diagram for this set, and then compare them and see that they represent the same area or the same set. So this is for A minus B, U, A and B. Okay, and we already know A minus B is everywhere inside A except the area that also falls in B. So this kind of area, that's A minus B. For the other one, U, A and B. So A intersection B prime. Let's do B prime first. So I'm going to use red for B prime. So B prime is everywhere that is not inside the circle representing B, right? The complement of B. So the entire rectangle except the circle representing B. So the red part is A prime, B prime. So I painted B prime red. And then A is obviously this circle here. So I've used this type of blue for A. Now we want to take the intersection of A and B prime. So the intersection of the area that is painted blue with the area that is painted red. Okay? And if you see, if you pay attention here, that area would be exactly the area that is painted blue here. So this is the Venn diagram for A intersection B prime, right? So again, these two diagrams, by comparison, you can see that these two sets are equal. Here's another example. So this time we have 3 sets. So it's going to be a little bit more involved. Universal sets, A, B, and C. Okay. Now, B union C. So I'm going to start with this part here. Okay. And let's say I want to use red for that. So B union C, everywhere inside of B plus everywhere inside of C. Right? That's union for you. B union C. And then take the intersection of that with A. So let's use blue for A. So this is A, the entire circle representing A. Okay. Now we are taking the intersection of the blue area and the red area. So it will be, I'm going to use a different color now, it will be everything here as well as here. Hope you can see that. Yep. So all this area will be yellow. Now, what we need to do is we need to do something similar for the other side. So for the other side, so this is A intersection B union C. So that's the yellow area. Now for the other one, again A, B, and C. We have A intersection B. So for all of this, I'm going to use blue. So the intersection of A and B is this area here. And then we have A intersection C. Let's use red for that. So A intersection C is this area here. And then we want to take the union of blue and red. So blue and red together, right? Which is exactly this yellow area on the left. So this diagram is for A intersection B union A intersection C. So for A intersection B union A intersection C, this area here, blue and red, is shaded. For A intersection B union C is the yellow, and you see that this is exactly the same area, which means that these two sets are equal. So that's how we can use, as I said, this is not a formal proof. That's a completely different story. but it's some type of argument for set identities using the visual representation of Venn diagram.